So the coefficients are 0. So a minus b plus d is 0. That's this constant term. The constant term is 0. And then the x squared term, which is negative a plus b minus d is 0. I'm leaving a space because there's no c mentioned. But technically there is a c in the matrix. It's just not part of the formula. And this is just a linear system that you're going to need to solve now for a, b, c, and d. Now, you can obviously tell, hopefully, that the second row is just a multiple of the first row, so you cross one out. And how many free variables do I have here?
2.
I see 3 free variables, which are
B, C, and D.
B, C, and D. Notice there's no C here, but that means it's free. It can be any number we want. So I'm going to just set those up, just because I like to switch my variables. So I'm going to let D equal T, C equal S, and B equal R. So R, S, and T are going to be my free variables. And then A is not free. I'm going to solve for it from the first equation, which is going to give me B minus D, which has turned into R minus T. So this is the A, B, C, and D. Okay, so would it be correct for me to then say that the kernel of T would be the set of R minus T, R, S, and T?
No, you gotta bust it up.
Well, no, hold on. Busting out the variables is how I would get the basis. But would this be correct to say that this is the kernel?
No, because you have to say within the set of all the numbers.
Okay, let's say I do that. You're right. Okay, let's say I say such that R, S, and T are real numbers. Now am I correct?
Still not correct because it's not a basis. Kernels have to be free.
Well, no, the kernel is a subspace, and I am being asked for a basis. I haven't come up with a basis yet, but before I do that, I'm just saying, before I bust out the variables and find a basis, is this correct to say that this is the kernel? I'm bringing this up because this is a point that a lot of people make a mistake on. The answer is no, this is not the kernel. Why not? The kernel is supposed to be a subspace of V. What is V?
A matrix.
What kind of matrix?
2 by 2.
2 by 2 matrix. If you're going to give me something in the kernel, you need to be giving me a 2 by 2 matrix. So a lot of times people will do this. They'll throw it into a column like this. This looks like a vector in R4 to me, the way I've drawn here. So I don't like that. What I need to do, if I want to write it correctly, is, I mean, it's not a big deal, but I just need to write the numbers in the right way. So the A variable would be R minus T here. The B variable is R. C is S, and D is T. So I would just want to write it like that. Okay, such that R, S, and T are real numbers. Everybody understand that? Make sure you're giving me kernel vectors in the kernel that look like vectors in V, because the kernel is part of V. Okay, now you guys have been begging me to bust out the variables, so I'm going to do that. When I bust out the variables, then I'm going to get my basis. Okay, so my basis now. My basis, so can you guys help me with this? What will be the first basis vector?
1, 1, 0, 0.
Okay, if we bust out the R, we'll get 1, 1, 0, and 0. Okay, what about when we bust out the S?
No, 0, 0, 1, 0.
0, 0, 1, 0. Okay, great. And the last one?
Negative 1, 0, 0, 1.
Negative 1, 0, 0, 1. Wonderful. So there we go. We have 3 basis vectors. That's my kernel. Okay? Awesome. Everybody good with that? Can somebody tell me, okay, so next thing is going to be the range. But before I find the range, can somebody tell me what its dimension will be?
1.
It's going to be 1, right, because the dimension of the kernel is
3.
Right, so the dimension of the kernel is obviously 3. We have 3 vectors here. Remember, the dimension of the kernel plus whatever the dimension of the range is has to add up to the dimension of V, which is 4. Right? So then the dimension of the range of T would just be 1. These two numbers have to add up to 4. It's just always nice to know ahead of time, like what you're expecting the dimension to be. We just like to calculate that in advance. Okay? So we just need a basis for the range, and it needs to have one vector in it. With me? Now the kernel, of course, was 2 by 2 matrices. But what's the range going to be looking like?
It's going to be W, so it's P2.
It's going to look like polynomials, right? So we want to make sure everything looks the way it's supposed to look. So our answer here should be polynomials. And do you guys remember how to find the range?
It's the span
It's the span of a set.
of the simplest basis.
So what we do is we find a basis for V and we transform it, each of the basis vectors. So we need a basis for M2 of R, and you really want to choose an easy one, like find something easy. So what would be like a good basis vector for M2 of R?
1, 0, 0, 0.
Yeah, so I would just use 1, 0, 0, 0, right? And then comma. I'm just making a list here. T of 0, 1, 0, 0. This is the standard basis. You're just moving the 1 around into different entries of the matrix here. Okay, so there's your set. T of each of those 4 things. Make some sense? Okay. And then you've got to evaluate all of these things, and I will be honest, sometimes this is not easy for everybody, so I just want to go through it carefully. To evaluate T of 1, 0, 0, 0, so Luis, could you pan back over here for a second? Sorry. So to do T of 1, 0, 0, 0, I'm just going to put in 1 for A, 0 for B, 0 for C, and 0 for D, and see what it gives me on the other side. So if I put in 1 for A, what am I going to end up with over here?
1.
1 minus x squared, exactly. So I put 1 minus x squared. Okay? Great. And now what about when I put in 1 for B? Minus 1 plus x squared. Minus 1 plus x squared. What am I going to get when I put in a 1 for C? 0. There's no C's on the right-hand side, so that's just 0. It's the next one on the list. And then when I put in a 1 for D, what am I going to get? 1 minus x squared. Okay, perfect. So this is what we have. But wait a minute, I thought you guys told me it was one-dimensional, and I've got 4 things here.
They're not LM.
Right, exactly. That means that these 4 vectors are LD. We've said this many times before, that when you form the span of something, of course they form a spanning set for the range of T, but they could be LD, so the dimension could get knocked down if there are dependencies there. And you can just look at this and tell me that there are dependencies here. Obviously 0 should never be in a basis. Throw that one away always. In terms of the other ones, well, if you know it's only one-dimensional, it means you need to just keep one of your vectors. Well, they all have to therefore be multiples of one of those vectors. You may as well just keep this one. Now, if you're not sure where the linear dependencies are with the set of vectors that you're listing, then if that's the case, remember what you had to do? You have to array those vectors into the columns of a matrix, row reduce it, and then throw away the unpivoted columns. That actually kind of goes back to the second midterm. That's a little bit older stuff. But that's basically what you would have to do if you couldn't just see it straight off. Okay, so this one, the range is just going to be, so this is going to be my basis right here. Okay? Does that make sense? And then can you tell me whether T is going to be 1-to-1, onto, both, or neither? Well, first of all, okay, back up. Again, remind me again, what is the dimension of V here?
4.
4, and the dimension of W? 3. So if V is bigger than W, what did we say earlier? We can automatically conclude?
It's not 1-to-1.
It can't be 1-to-1. Now, of course, we know that because look at your kernel. Your kernel is not trivial, right? So it's not 1-to-1. And then it might be onto. Now, is it onto?
No.
No.
No. What's the quick reason why it's not onto?
There's no, right? And it's not the same dimension.
It's not the right dimension, would be what I would say. This is supposed to be 3-dimensional. P2 of R is 3-dimensional, but I only got a 1-dimensional range. Not big enough. That make sense?
Yeah.
Incidentally, if we had done a problem, okay, I'd have to change my example for this to work, but if we had done this example, and let's suppose that the kernel, let's just do this as a follower. I like this. Actually, I could make this into a theoretical problem. Here we go. Assume t from m2 of r to p2 of r has the dimension of the kernel of t equal to 1. Prove t is onto. So this is theoretical. I'm not even really giving you the formula here. I'm not telling you what the transformation actually is, but let's just suppose I gave you that. I'm going to give you guys like 30 seconds to kind of stare at that. Try and think through in your mind, how would you convince me that it has to be onto? Just a second. Now remember what you have to remember what onto means. If this is a question on the test, the first thing you're probably going to want to do for partial credit is remind me what onto means. You explain what you're trying to explain, even if you don't know how to explain it. Tell me what it means, and then you have to figure out how to justify it. So how many of you think that you know how you could explain this? Just 2.5 people. Take another 30 seconds. I'm going to try and get everybody on board with this. The transformation, the kernel is one-dimensional. Brian, do you think you know? No. Okay. Frank? Give it a try.
You can use the formula, the dimensions of the kernel plus the dimension of the range.
Okay, good. Exactly. So if the dimension of the kernel is 1, then what's the dimension of the range?
3.
Right, so the dimension of the range has to be, well, it's 4 minus 1, right?
Yeah, so
It'd be good to write it as 4 minus 1, because then you're showing your work. I see, oh, it's 4 and this is 1. Subtract them off. You get 3. Okay, good. So the dimension of the range is 3. Okay, what else do you need to say?
That if it's onto, then the dimension of w is equal.
Okay, maybe what we should do is write down the dimension of w. What is the dimension of p2 of r?
3.
That's also 3. So the range and w are both 3-dimensional. What does onto mean again? This would be worth some partial credit as well. Below?
Dimension of the range of t is equal to the dimension of w.
That's true, but actually if I was to ask you what does onto mean, I probably would just simply say that without even talking about dimensions, the range is equal to w. So the range equals w. Can we conclude that here? Well, look, the dimension of the range is equal to the dimension of w. So if they have the same dimension, they're in the same universe, they have to be the same. They have to be the same thing, right?
Yeah.
So range of t equals p2 of r. This wouldn't be that bad of a question, right? Could probably handle that. Just explain it. Lots of potential for partial credit. Each little thing you're writing down is worth some points, so you want to try and put all that down. Okay, great. Yeah, so this one ends up being neither. I forgot to conclude that. It's neither because the kernel is not trivial and the range in this example was not the whole space. You guys want to try one more example of that? Should we do that? Yeah, let's do one more example and then we'll see what you guys want to, what else you want to cover. I haven't done anything with annihilators yet. Might be a couple other good problems on the sheet. And then, if we're getting tired, we can always call it a day. Or I can keep going. I'm good with whatever. Let's do number 10. I think this is a really good one because it's a little more abstract than the previous one. So this is good practice. Let's suppose we take t from p2 of r and map it to p2 of r. And t of P of x is equal to x P prime of x plus 2 P double prime of x. So getting this one started is a little bit important here. Same question. Let's find a basis and dimension for the kernel and the range. And just like before, I think I'll start with the kernel. Oh, by the way, if I ask you, is T one-to-one onto both or neither, what would you be able to tell me right now before we even do anything?
Both or neither.
It's either both or neither, right? Because V and W are the same dimensions. Okay, so it's either going to be both or neither. All right, let's start with the kernel part. Now, when we do the kernel part, what we're doing is we're taking the transformation and we're setting it equal to 0. And then we're trying to solve for the P of x. Is that something, how are we going to do that here? Yeah, this is the key, guys. You see the difference between the two examples? The example that we did before, everything was very explicitly written out. All the entries of the matrix, all the coefficients of the polynomials. This is kind of being put down in a more vague form. Just P of x is all it says, right? In order to really get anywhere with this, what you're going to need to do is you're going to need to write out what your P of x looks like as a quadratic polynomial. So this is a key step that some people get confused when they don't write that down. So just put it down as a quadratic polynomial. Ax squared plus bx plus c. Okay? That's going to make it easy to then tell me how this transformation really works. Because now I can say, all right, so T of P of x, I'm not finding the kernel yet. I'm just trying to rewrite my expression. So what is it? It's x times the derivative of P of x. See, now I have something I can actually differentiate. So what would be the derivative of ax squared plus bx plus c? 2ax plus b. Excellent. Okay, so we have that. And then plus 2 times the second derivative of P of x. What would be the second derivative?
2a.
2a. Great. Okay. And I might even want to clean that up a little bit. So this is 2a times x squared plus b times x plus 4 times a. Okay, so this is my, now I've expressed my inputs and outputs in a little bit better form. Okay, so now when I'm trying to find the kernel, see, instead of trying to set this equal to 0, which is actually kind of hard to do, to solve it for P of x, this is going to be a lot easier when I set this one equal to 0 to solve it for x, to solve it for P of x. So if I know that 2a x squared plus bx plus 4a is 0, what can I conclude from that now? You know what some people will do? They say, oh, I'm going to use the quadratic formula and solve for x or something because it looks like a quadratic. Don't want to do that. We don't want to do that, right? We're not trying to solve for x right here. Okay, guys, x is not a number. We're not putting a value in. X is simply a placeholder here, the x and the x squared. So each coefficient, right, the constant term, the x term, and the x squared term, they each have to be 0 in order for it to equal 0. We're basically equating the two sides of the equation. So what we're going to get is 2a has to be 0, b has to be 0, and 4a has to be 0. All of those things have to be true. And that's really simple to deal with because it just tells you that a and b are 0.
Yeah.
And the only thing that's unknown about is c. So if you come back up to what is your polynomial, if a is 0 and b is 0, then your p of x is just a constant. Right? So the kernel of t is just the set of constants. It's just the set c such that c is a real number. If you want, you can put it as a free variable and call it t. Same difference. And so what is going to be a basis for the kernel of t? If you bust out the variable, usually when you're finding a basis, you bust out the variables. So over here we busted out the r, the s, and the t to get these three things. What do we have to do here to bust something out?
What's up to C?
Bust out the C, leaving you with 1. There you go. That's it. Basically, the kernel is just the constants. Anything that's a constant function, when you plug it into this transformation, it's going to get killed because you're taking derivatives of it. Okay? So the basis is just the set 1. What's the dimension of my kernel then? 1. Okay, so the dimension of the kernel is 1. Dimension is 1. So let me just stop right there. So is this transformation 1-to-1 onto both or neither? I haven't even done the range yet, but I think I can already answer it. Yeah, see, it's not 1-to-1 because the kernel is not trivial. So if it's not 1-to-1, remember we said it was either both or neither. So if it's not 1-to-1, then it's also not onto, so it has to be neither. So we know that already. It's got to be neither. Okay, so it's neither. And the only thing left to do is to try and work out the range. Do that right here. What's the dimension of the range going to be? 2, right? Kernel plus range adds up to the dimension of V, which is 3. So the kernel was 1-dimensional, so the range, we're expecting it to be 2-dimensional. Put that down here. The dimension of the range of T is 2. Okay, so we know that much. Great. And so then it's just a matter of finding the range. So the range, again, we're just practicing it one more time. It's the span of, what I have to do is I have to transform a basis. What's a good basis for P2 of R? So transform. Polynomials. You want to have a nice basis.
X squared, X equals 1.
Great, x squared, I like that. So we're going to transform x squared, we're going to transform x, and we're going to transform 1, right? Those 3 things, exactly. So there you go. Transformation of those guys. Okay, so now we have to calculate these things. Now, we have a couple of choices here. We can either transform them from the original thing that was given here, which was more abstract, or we later rewrote it like this, basically, right here. So we can transform it using either formula for t that we have on this board over here. Which one do you want to use? It doesn't matter. You like the second one? Okay, so for the second one, when I want to transform x squared, I have to choose the right numbers for a, b, and c. So if I want to transform x squared, what am I going to put for a, b, and c here?
One, 0, 0.
Right. A is 1, b is 0, and c is 0. That's how you get x squared as your input.
Mm-hmm.
If you're not liking this, you have another option. Okay, you can always use this formula. But this is good because sometimes you have to do this. So if you're trying to figure out how to plug in x squared into the transformation, and this is what your formula looks like, you have to choose the a, b, and c that you're going to use. So a is 1, b is 0, and c is 0. If I plug that in down here, a is 1, b is 0, and c is 0, then what am I going to get for my answer?
2x squared plus 4.
2x squared plus 4. Does everybody see that? The a is 1, so this is a 2x squared, and a 4 here, and the b was 0. So just to be clear here, guys, this x squared is 0, I'm sorry, it's 1 times x squared plus 0 times x plus 0 times 1. 1, 0, and 0. Those are the values of a, b, and c. So I'm putting those numbers into that second box formula near the bottom there. So if I put in 1 for a, 0 for b, and 0 for c, I simply get 2x squared plus 4. That's the first one. You could also have gotten that from up here. If you differentiated x squared and then double differentiated it and just simplify the expression, you'll get 2x squared plus 4 that way as well. Okay? Now for t of x, now I have to put 0 for a, 1 for b and 0 for c in my polynomial, right?
Yeah.
So b is 1. So if I look at this equation and put b equal to 1, what am I going to get for an answer?
X.
X. Great. Okay, just x. And then the last one, t of 1,
Just 0.
it's just 0. There is no c anywhere, so that's just 0. So if I'm looking, so I know, see, this is where it's great if you know the dimension of your range. You know you need 2 vectors, but there are 3 things here. It means you need to throw one thing away, right?
Yeah.
What are you going to throw away?
The 0.
The 0. So your basis is this part right here. Now, if I had 3 things, let's suppose it was 2x squared plus 4, and I don't know, 3x squared minus 5, and 5x squared plus 8, or something like that. What if it was those 3 things? Is it so obvious what to throw away? See, if it's not so obvious, see here you know 0 is not going to be in a basis. So we're getting away easy here. But what if it wasn't? What if I had a list and it wasn't so obvious? Then what you have to do, remember, is you have to take these vectors, slam them into the columns of a matrix. So the 2, there's no x term, and a 4 constant term, and then a 3, and then a no x term, and then an x squared term, and then a 5, and a 0, and an 8. You have to do this. This is how you sort of check your linear independence thing. And you work it through, and you find out there's a pivot there, and there's a pivot there. Okay, great. That means this is an unpivoted column. That means you get rid of that vector. I don't want people just like randomly throwing things away just to get the dimension to come out right. You have to throw away something that is linearly dependent from the list, because sometimes people will make a mistake and throw away one of the vectors they were supposed to keep. Here it's easy to not make a mistake, but sometimes you might have to do a little more effort to get the right thing. Clear enough? Okay, so that's that. So that's the basis for the range, basis for the kernel. So this is kind of what you need to do. Practice a few more of these. On the kernel and the range, I think you'll be in pretty good shape. Okay. I think what else I want to go into here. So 6A was on the group work. Well, I could do a couple more. I'll do a couple more problems off this sheet, and then I'll just see if everybody's got energy to keep going or not. Let me. I guess I'll come back over here again and use this one. Everybody keeping their energy up? Should have brought my coffee maker, except I don't drink coffee. That's the problem with that. But yeah, kind of late night on a Thursday. It's like, it's been a long week, hasn't it? It's been a really long week for me because I hurt my foot, so walking everywhere has been painful. And so I'll be anxious to lounge around by the time Sunday. Guess why you guys are taking the test on Monday? I can just kick my feet up and relax. I don't have to walk. That'll be nice. Okay, so number 7. Show that x e to the x is an element of the kernel of L, where L is equal to negative d squared plus 2d minus 1. Just practice this one real quick. Okay. Guys seen problems like that before? What chapter does it go with? 5, 6, or 7? Is there anything with differential equations here? Does this have to do with differential equations?
Yeah, the D2.
Yeah, we have derivative. Okay, so then it's chapter 6 or 7.
Yeah.
Is it scalar? Are we talking about scalar functions, or are we talking about vector functions? Because that tells me which chapter it is. It's a scalar, right? This is just a scalar function. It's not a vector. It's just a function, scalar function, calculus function. Okay, so it's chapter 6, right? It's chapter 6, and we're just trying to check whether x e to the x is in the kernel of that. So how do you check that?